This problem can be solved in a very simple way. Let's look at some trivial cases before we move on. So let's pretend there's only two people, so we're going to ignore these two people. So if there's just orange and blue, what's the probability that blue, who's the last person in line, gets his seat? It's easy to see it's 1/2, because either orange goes here, which is great because blue gets his spot, or he goes here, which is horrible because then blue does not get his spot. Let's think about it with 3 people, which might require us to do a little bit of calculation. So first, the probability that orange goes to orange and everyone's happy is 1/3, because then blue can go to blue and green gets his spot. That's 1/3. Now that's one case to get success. What's another case to get success? What if orange goes to blue's spot? Then that's a 1/3 probability. And let's actually write this down. So the first case of success we saw is 1/3, where orange goes to orange. The next chance of success is if orange goes to blue, which is 1/3, and blue does not go to green, so he goes to orange, which is a 1/2 chance. And those are the only cases of success, because if blue goes to green, then it's all over. So if we just total up this little product and sum, it comes out to 1/2, which is good. We're seeing that there's a 1/2 pattern. And in fact, the answer to this problem for any number of people, any n, is 1/2. Let's see how to get that using easy way instead of complex probability calculations that are going to go horribly wrong. So we're going to think of this as, we're going to change this problem a little bit, but have it be the same problem. So we're going to seat everyone. Everyone goes to their seat. Now, this is the same problem if, let's say, orange hurriedly runs off to the bathroom and comes back, and then he just rushes into some random seat because he's crazy. So let's say he just rushes into blue's seat, which forces blue out. Now blue is displaced, and we're going to use that word meaning it doesn't have a seat. So he's displaced, meaning he has nowhere to go. Now he just rushes somewhere else. So let's say he rushes into green. Notice he can't rush back into oranges because he's already set. So once someone rushes into somewhere, they're already set. And I'm going to indicate that by having them on the line. So he can either choose to go to orange, green, or red. So let's say he rushes into green, and now he's set. Now green is displaced, and now he can either go to orange or red. If he goes to orange, then red can stay where he is because no one else needs to get moved. But if he goes to red, then red loses and he doesn't get his seat. Remember, this problem is all about red. So we're going to reset them. Now we want to find the way to find our answer is the same as finding what is the probability that orange gets filled first versus red gets filled first. And let's explain that with actually writing. So we only need to worry about 2 cases, case 1 and case 2. Case 1 is the probability that orange seat filled first. And case 2 is the probability that red seat is filled first. And by filled first, I don't mean filled as the very first seat. I mean it's the first one to get filled out of the 2. So what I mean is, so let's do this again. So orange goes to the bathroom, comes out, and now orange can go to blue seat, in which case blue goes here. And now if blue goes to orange's seat, then he has fulfilled condition number 1. If blue goes to red seat and displaces red, he has fulfilled condition number 2. That's what I mean. Whichever one out of the 2 gets filled first throughout the course of a round. So what is the implications of each? So if the red seat gets filled first, which means that the orange seat is just vacant, and whatever's gone on here, who knows. But let's say that the red seat gets filled first. That means red has lost, because he has lost his seat to someone, and it's all over. So that's pretty obvious to see. But what does condition number 2 imply? So what is, condition number 1. What does the condition that the orange seat is filled first imply? To do this, we're going to use a little bit of logical thinking about cycles. So think of it this way. Here's orange. Now orange, when he gets out of here, goes to the bathroom, he has to displace somebody. Either he goes to his own seat, so that's one case. One case is that orange goes to orange's seat, in which case everything works out. But the more likely case is that he goes somewhere else. So he goes to some person P1. So that could be anyone. Now P1 is displaced. They have nowhere to go. And so they have to go to some person P2. And now, and by person I mean that color. So let's just do a simulation. So orange comes out, and let's say P1 is blue. So goes to blue. Now he has to go somewhere. Let's say he goes to green. Whoops, flew out of there. It goes to green. So green is P2. Now green has to go to some P3 and so on. Now, if any one of these is orange itself, then we have a cycle. So let's say P3 is orange itself, which means that green goes to orange's seat. And P1, P2, and P3 aren't people, they're the color. So he goes to orange's color. And this cycle, so let's indicate each of the people. This was blue, I think, and this was green. So notice this goes orange, blue, green, orange. So it's a cycle, and the cycle is orange, blue, green, orange, blue, green. Notice that cycle does not involve red. Red has not been touched. The seat has not been rushed into, which means that red is fine. And that is what condition 1 implies. So if we can get a cycle like this, P1, P2, P3, and going to end seats P4, P5, P6, P7, all the way to, as many people as you want, and none of those people are red, which ensures that condition 2 is not fulfilled, then we have then red will be okay. He'll be able to stay in his seat. As long as the orange seat is filled first, we have a success. So now after all that talk, we're going to finally get to the decision. Since there's only two cases, orange seat filled first or red seat filled first, and each one has an equal likelihood of being filled throughout the game, that means that our probability is 1/2, because each of these